Does it work? Right, yeah, so we are a bit late. Again, it's a great one to Frank. I think Frank does not need any detailed introduction, but I would like just to say that one thing that maybe we don't, this is just a personal thing for me that I found very fascinating about Frank is that he has worked on so many different topics. So he started with QCD, and he did one of the most important work in QCD that got him the Nobel Prize. And after that, he moved to black hole physics as well, after doing also many studies in particle physics. But also in the recent years, he's working a lot in quantum matter physics. And not only that, he also introduces not only new concepts, but very nice names. Like for instance, axions, time crystals, anyons. And so not only he introduces very interesting concepts in physics, but he can also give nice names that help people somehow getting what is going on, even from outside the community. So in this sense, we're very happy to start this conference with Frank. And as an association, on behalf of everyone, we thank you very much. So please, Frank, first it's yours.
Okay, thank you. So, to align myself with the role of starting things off and giving a keynote speech appropriate to the 100th anniversary of quantum theory, I decided to talk about how quantum technology meets fundamental physics. And there are many, many things one could discuss under that heading, but I'm going to pick three that I think are very compelling and that I've been working on, so I know something about it. So I will talk about gravitational waves, T violation and axions, and then intensity and thermometry. And these will all weave together too. So gravitational waves are produced by gigantic sources in the sky doing tremendous things, but the signals are very, very tiny because space-time is very, very stiff. And that means that to rise to the challenge of detecting gravitational waves has been a big enterprise. It took almost 100 years to detect gravitational waves at all. And I'm going to suggest that the next generation or two of gravitational wave analysis will be enriched further by quantum concepts. So this is an indication of sort of the anticipated gravitational wave spectrum. There may be more that we haven't really anticipated yet. For instance, there are speculations about cosmic streams. But here are some semi-reliable sources of gravitational radiation. They typically are on long timescales by particle physics standards, and they are accessible by a variety of very different techniques depending on the wavelength, because the wavelength spans an enormous range. One that I think is quite remarkable and that has reported results recently is pulsar timing. The idea here is you survey many pulsars, which are spinning objects that act as fairly reliable clocks, and you compare them with clocks on the ground that are super reliable, and look for the signatures of distortions of their ticking and their position in space through radio telescopes. So we'll view the details of radio telescope technology, except sitting at the middle of every radio telescope is a maser, a quantum device, and the clocks that are involved here are atomic clocks. So it's quantum mechanics all the way down. And here is the recent result that was reported, where there is evidence that the very, very long wavelength gravitational waves they tried to access, in fact, fact do occur, you see this signal needs work, and in future years will improve, but they already interpreting this as some hint, some indication of mergers of supermassive black holes that we know exist at the center of many galaxies, or maybe the process of building them up. The strategy for gravitational wave detection that has borne the most fruit so far is the use of interferometers. And the basic idea is very simple. You look for distortions in space and time by monitoring some test masses. Details are very, very impressive. The distortions are a part in 10 to the 20th, 1 part in 10 to the 20 or less. So you have to go a long way away and bounce the light many times in order to get a distortion which is very, very tiny, a fraction of an atomic nucleus. To measure that is quite a challenge. You need very precise mirrors, you need very precise lasers, you need very precise clocks, everything. These are the facilities, they're gigantic. These were the original, so now they're sprouting all over the world. These were the ones that made the initial observation in the far northwest and the far southeast of the United States. And because the wavelength is so long, they should both see the same signal. And this was the initial discovery. Now there are hundreds of events seen, interpreted as black hole mergers, also mergers of black holes and neutron stars, also even in one case, the merger of 2 neutron stars, which is especially interesting because neutron stars are kind of the distilled essence of and challenge of QCD. We should be able to calculate their properties, but at present we've failed spectacularly at that task. It's quantum theory, if you will. An early technology for accessing gravitational radiation was proposed by Joseph Weber. That is the use of resonant bars, this big, very stiff bars that in response to the quadrupole distortion set up by a gravitational wave should vibrate. And you can calculate from first principles what to expect for a given vibration. These, for a given incident gravitational wave, and now we know what the gravitational waves are, at least some sources. And we know that the intensity, the interferometers are more sensitive, but the bars have a significant advantage in that they give a digital signal. It's also an advantage that they're not so sensitive, so they're on the verge of clicking or not. And that means that noise and fluctuations are very significant. And so these are the digital things that can fire or not, and they give access to the quantum aspects of gravitational radiation. And they are the requirements for bars that are capable of detecting excitations or registering excitations that are detectable in response to the kind of signals detected at LIGO are not outrageous. So it should be possible to make several of these things, take advantage of the long wavelength, and get new information about the gravitational waves. I just gave a series of 4 one-hour lectures at our Quantum Connection Summer School outside Stockholm on this subject, on what kind of information about gravitational radiation you can access from these kinds of measurements. And the takeaway message, the big takeaway message is that you can make quantitative tests of the rough idea that gravitational wave is classical. Gravitational wave is classical, which is the default assumption in the literature. The precise form of that is that gravitational waves are described by what's called coherent states in quantum mechanics. And so the coherent state hypothesis is the precise version of the intuitive version, statement that gravitational waves are classical, and this hypothesis can be decisively tested, and there are reasons to think that it fails. So this is, I think, an important part of the future of gravitational waves being confronted with quantum mechanics. How am I doing for time? What? Okay, this is a kind of methodological slide, which I'll come back to in this, but maybe more suitable for questions or discussion later. People talk about quantum gravity, but they mean many different things, and I think it's useful to distinguish. The only thing I'll mention right now is so we can make comparisons between how we discuss quantum gravity and how we discuss electromagnetism, which is in many ways a simpler theory, and the level of analysis that I lectured about and just mentioned previously, I would say is at the level of quantum optics. But the methods that we use are the methods of quantum optics, but applied to gravitational waves. Okay, so next case study, I want to discuss time reversal, symmetry violation, and axions. So a deep aspect of our understanding of fundamental law, and perhaps an explanation of the dark matter that cosmologists need. So the two questions are, how much is T violated? And another question. But here we have a rich and partially triumphant story. How much is T violated? In the segment of fundamental physics that deals with flavor changing processes, things like KK bar mixing, heavy quark decays, and so forth, T violation, usually in the form of CP violation, but I'm going to assume, as sane people do, that CPT is not violated, so CP violation is equivalent to T violation. In the delta F, delta flavor not equal to zero sector, we have a brilliant theory due to Kobayashi and Moskawa. They identified that in the standard model, when it's extended to contain three families, you get one and only one parameter to discuss flavor changing time reversal violation. And at the time, the third family wasn't known, predicted it in real sense, and all the subsequent phenomena of T violation involving heavy quark decays and so forth have confirmed their theory, their one parameter theory that was fit to phenomena in K-mesons. But maybe fortunately, they didn't realize that the standard model also supports another form of T violation in the flavor non-changing sector. This is the famous or infamous theta term of QCD that violates parity and time reversal, but does not change flavors. And its absence, or the fact its possible presence is a real embarrassment. It's an imperfection in our understanding of the world, because we know that its strength, its numerical magnitude, is much smaller than it sort of should be by dimensional analysis or reasoning from what's reasonable. So, but the phenomenon is that if you have the phenomenon that doesn't happen is that if you have a spinning particle, it does not induce charge separation. So if you spin a fundamental object, it all spins spontaneously in quantum mechanics, you don't induce an electric dipole moment. And the only explanation of this that's quantitatively adequate, the only sufficiently good symmetry to possibly explain this is time reversal symmetry. That does explain it, because if you apply time reversal to that picture, you get a reversal of the direction of charge flow, and so the opposite effect. So time reversal is good symmetry. This can't happen. And this is a whole subject in itself, to try to measure fundamental electric dipole moments. And all I'll say about it is that if I were a young experimentalist, I would seriously consider looking into this. And there are different technologies and different approaches, but all of them make use of cutting-edge quantum technology. Now, so that's how good is T. Then the other question is, we already know it's very good. Quantitatively, it's about 10 billion times better than it should be in this sector. The theta angle is bounded by that pure number that could be over 1. So why is it so good? And the best theory we have for this is a theory of evolution. So it's something fundamentally new in our description, I think, of basic interactions. And with minor modifications, there's a unique theory of how this works. You have a complex field that, in the course of the history of the universe, starts out at very high temperatures, at the excited and on average at 0 value with a big spread. As the temperature cools, energy starts to compete successfully with entropy, and it rolls down the hill. And this is all taking place in a simple modification of the standard model to accommodate something called Paget-Quinn symmetry that gets spontaneously broken. You roll down here, and as the universe gets colder and colder, the amount of energy involved in departures from the minimum value gets more and more profound. So that forces the field to, first of all, rather rapidly decrease in magnitude, but then more slowly decrease in phase. And at the bottom here, you have enhanced symmetry, so that's where T violation is good. So this theory of evolution explains why T violation is so good in the world dynamically. But there are some oscillations left over at the end. And just like the gravitational field, because the field involved is very stiff, even small oscillations in its magnitude can carry a lot of energy. And if you run through the consequences of this scenario, you find that this residual energy in the field that's trying to settle down to the symmetric point, with residual energy, is enough to make the dark matter of the universe. And it sort of fits the bill in more ways. So this is something I call an axion. There's a story that goes with that, but it really was named after this laundry detergent. And I told the editors of Physical Review Letters that it's because it cleans up a problem with the axion current and gives the fit. And it's become now an enormous enterprise throughout the world with dozens of serious experiments to try to detect this background. Part of its success as a dark matter candidate is that it interacts very, very feebly with ordinary matter. So that's true. But we'd like to see a positive indication of its indication with ordinary matter. And a strategy that's been very popular and seems to be interesting as a possibility for detecting the background is that there's a basic coupling of the axion to electromagnetism in the form A times E dot B. So the axion couples to electromagnetic fields, and in the presence of a background magnetic field can convert into photons. So the name of the game here is, first of all, to get a really good eye, because the human eye is not adequate for possibly microwaves or even longer frequency, longer wavelength, but also the human eye is not sensitive. But I mean, the other thing is, but this is the spirit of the thing, and the other thing is you want to enhance this conversion as much as possible by using tricks of resonant cavities, filling the cavities with suitable metamaterials, every trick in the book to try to get a detectable signal out of a very, very weak predicted color. So people have thrown all kinds of ideas at this, and you see there are many, many, many competitors here. Each few of the lines in that forest of helioscopes is another experimental group. There are other proposals. There's astrophysical evidence. So far, no detection, but that's okay because the golden region where this one parameter theory predicts has barely been accessed, and especially the blue band where it's predicted quantitatively to provide the dark matter cosmology. Significant uncertainty, especially in the latter, but you see that the experiments are getting very interesting, and these future things, the pink, are actually getting there. I'd just like to show you a representative trick that shows quantum technology at work. Well, whether you call it quantum or not is sort of a matter of taste, but it's modern, tricky electrical engineering, and then there are quantum detectors at the end. This is a metamaterial that is designed to encourage axions to convert into electromagnetic fields, and the innovation in this one, which we're about to publish, is to break these bars into two, the earlier designs, and just continuous wires or bars inside. And it's all inside a box, so it's a resonator. And here's the field profile. You see, you get concentrations of electric field in the middle, which make it more detectable. What the axion does is basically drive currents. And so if the currents, if you have these bars, the charge accumulates at the ends and makes big electric fields. And that's what we're trying to detect. We saw boosted E fields in this simulation. And then, oops, We can combine that with another idea. Now, in the case of gravitational waves, as I showed, the original strategy at Weber was to do absorption of gravitational waves, basically, in these bars. But the winning strategy was interferometry. It's possible that history will repeat itself. In the case of axions, you could also do interferometry. The basic strategy is this. You have, again, a basic interferometer with two arms, and you want to detect the influence of axions, in this case, on light travel through one of the arms. And the key is to have what's called an electro-optic material there. These are materials that have nonlinear response to electromagnetic waves. So at a formal level, inside the Lagrangian, you have an E cubed kind of term inside the material. The axion, as I mentioned, if you coax it the right way, will produce big electric fields. And so, well, big is a relative term, big meaning less than infinitesimal. And the idea is that if you have a modulated E field, so if this electro-optic material is inside one of these resonators, you actually would want to use a rather different design, but the same idea, then the E cubed becomes a time-dependent E squared, which is a time-dependent index of refraction, which is, of course, the bread and butter of an interferometer. The light has a different index of refraction, both this bit and that bit, a time-dependent index of refraction. So that looks very promising. And then before leaving the subject of axions and quantum technology, I'd like to mention a very recent publication where people have succeeded in a real tour de force of condensed matter physics, at Harvard, in designing materials that have excitations. I call them quasi-worlds because if you lived inside the material, you think that's the world. Things behave different, you have different kinds of particles. In this quasi-world, you have particles that really do obey the equations of axions, different values of the parameters, but they really do. So this nature is not averse to realizing this idea. Okay, now how much time do we have?
7 minutes.
7. Excellent. That's a lucky number. Okay, intensity interferometry. So, this is an old idea, intensity interferometry. It goes back to the 1950s or maybe even 1940s, but it's an idea whose time I think it may have come because it's been limited by technology of photon detection and sensitivity, and now and information processing. Now we can do better, and these things may be coming together, similar to the drives of neural nets. So this is the basic HBT. HBT stands for Hanbury-Brown twist. The two radio astronomers who pioneered this idea and should have gotten the Nobel Prize but didn't. The basic idea is this: you have two sources and two detectors, and you look for correlations in the intensity measured by these two detectors. And according to the rules of quantum mechanics, you're supposed to add amplitudes in that square. That means you have this cross term. The cross term is what's different, and that is correlative. That means correlations. Otherwise, you just have the terms that are direct product of intensity. And this has various advantages. Given the limitation of time, I won't elaborate on these, just to say that I'll be showing you shortly how this kind of detector can work in very challenging environments. And this is why. basically, well, just I have some actual equations in this talk. Okay, so this is what we have for the intensity correlation as a function of a time interval at two different places, A and B. We want to measure the electric fields there, which produce the intensity. And so at the level of quantum mechanics, this is the rigorous expression. This is the sort of thing that Boyd Glauber contributed to the discussion and did with the Nobel Prize. We expand these electromagnetic fields into modes as excited by the source, and then this is what we have to evaluate if we want to evaluate the intensity correlation. And to simplify things for a first go, if we put the two detectors at the same place and just measuring intensity fluctuations and at zero time, then if we have a lot of independent modes contributing from 1 and 2, the expression looks like this in terms of creation and annihilation operators for those different modes. And you'll see that because we have not only the naive way of getting intensity, but also this kind of cross term, we get a factor of 2. And that was the great discovery of Hindenburg, which was this extra factor in intensity fluctuations. That very nicely realizes the intuition from the photon picture that you can have a new process that where the Bose statistics doubles the amplitude. So to square it, you get a factor 4. But there were 2 processes. You had 2 before, so it's a factor 2. But in the other extreme, if we have only one relevant mode, as we do for classical light, or the light coming out of the laser beam, there's only one mode, there's no such doubling. You just get one. So this is a lovely example of why in quantum mechanics you have to be careful. In particular here, thinking about photons. That's not the right way to think about electromagnetic radiation in this case. It's, you have to think of it as the field. And in the gravitational case, it's supposed to be coherent. It's supposed to be just one mode, classical light. That's the default assumption anyway. And you can get more information if you separate the detectors or separate the time, or that. That's what they actually used. They use this to determine the radius of Sirius originally. And we don't get an image, we get information we can process. So and the intensities are very small. That's why it's been a challenging technology. So now, with that background, a couple of new things. This just appeared in Physical Review Letters. And the idea is that to extend intensity interferometry to non-luminous objects, this could be in microscopy, or also could be remote detection, as you'll see. We need to supply them with light. And lasers are very good for that, but they produce coherent light, and that's too good. There's no fluctuation. So the solution is to mess it up. Inject noise. And following that strategy, you can also do it for free. You can propagate beams through a turbulent medium. Or you get some help, I should say. I said you don't need delicate laboratory conditions or telescopes that are very stabilized, and so we just measure this kind of junky wave intensity correlations. Across the city, this is 1.36 kilometers in Shanghai, which is not as polluted as Beijing, but still. And you can get sub-diffraction limited resolution of targets. And then coming back to gravity waves and testing the coherent state hypothesis, coherent waves should have no fluctuations in this context. If you see fluctuations, that's proof that it's not a classical, maximally classical coherent state of the gravitational radiation field. Finally, let me mention that this technique of intensity interferometry can be taken into other realms. There are applications in condensed matter physics, for instance, and one that's borne fruit recently it's not exactly what's pictured here actually, but it's the same idea, is that you do setup with two sources and two detectors and look for intensity correlations, in this case correlations of currents on the two sides, and that can be sensitive to the relative phase accumulated by particles moving in these two different ways. In this way, experimentalists found direct evidence for the existence of particles that are neither bosons nor fermions, so-called anyons, in the fractional quantum Hall effect. So, those are my three case studies, and I think they really give new meaning to the poetry of William Blake, who said to see the world in a grain of sand and heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour. I think that's poetic, but it's also, if you replace a grain of sand by a quantum detector and a flower by brains and ingenuity that it holds, when you invoke quantum mechanics to learn about basic features of the physical world through the wonderful modern technologies that are becoming available. That's quantum connections. Thank you.
Thank you very much, Frank.
So I just sit down now, or questions?
Yeah, let's see if there are just one or two questions. Yeah.
Hey, thanks. Thanks for the talk today. What about high frequency gravitational waves, which is now taking?
Yeah, well, this works very well for high frequency. The bars are, yeah, you can. They're sort of more natural at the higher frequency end. But there we don't know what sources there are, if any. That's the problem.
There is one last question.
Frank, fantastic talk, thank you. I just wanted to make a quick connection with the early universe that's also being tested by gravitational waves. Another interesting phenomenon would be first-order phase transitions in the early universe, where there are bubble collisions resulting from what's after the phase transitions, which could also give stochastic gravitational wave signals that may have been seen. So there's fun connections.
There's clearly a bright future for the field of gravitational wave detection. I hope hope quantum mechanics is going to be a big part of it. So we expect.
We'll also have more time for questions during the Q&A session plus discussion. So if you have more questions to Frank, you can ask it later. Okay. So let's thank Frank again.